welcome to the House of ZK Radio, which is a focused podcast and media channel exploring everything ZK, zero knowledge. I'm Alice, education lead at ZKM. Today I'm joined here with co-host Pavel, who is DevRel lead at ZKM, and our guest Jeremy, who is CEO of RISC Zero. Thank you so much for being here, Jeremy. We're very excited to have you.
Absolutely. I'm happy to be here.
Yeah, I'm wondering, Jeremy, if we can first start off with your story on how you first got involved in the Web3 and specifically the ZK spaces.
I have been an entrepreneur pretty much all of my life, as well as a technologist. I think I first started programming when I was about 6. I've particularly really love mathematics, and I actually read a lot of math research papers just for fun. And sort of the focus of all of my companies, while they're across a bunch of different fields, bioinformatics, machine learning, have all really focused on this idea of taking an existing sort of emerging mathematical research, like something that's being newly discovered in sort of the mathematical side of the world, and realizing when it's practical, when it's applicable, and sort of helping to sort of productize that, right? So I've actually been following, ZK for, probably 7 or 8 years now, because it was, clear to me that the potential impact was really huge. The idea that you could verify an arbitrary amount of computation in an instant was, to me, just mind-blowing when I first heard about it. But it was also very clear when I first looked into it that performance-wise, it was nowhere near where it would need to be practical. Obviously the programming models were really not reasonable. But I continued to follow it. And then while I was working at Intel, after they had purchased my previous machine learning startup, I think it was really with the emergence of Elie Ben-Sasson's work on Starks that I became clear to me that it was getting to the point of being practical, at which point I started doing a lot of implementation on GPUs to kind of get an understanding of where the performance would eventually get to. At that point, I was I got super excited because to me, it was clear the performance was going to get to a practical level. I started to try to get all of my other sort of, startup friends also excited about it. But when I talked to them, they were like, well, how do you program it? And, I was like, oh, you just, write some polynomial constraints over, finite field elements, et cetera, et cetera. And they're like, what are you even talking about, Bruestle? And, so I think that it became very clear to me that in addition to sort of the performance concerns, which I'd always been concerned about ZK, that the next concern was really this sort of usability concern, that it was not reasonable to program in ZK. And so, I continued to keep thinking about it. And then, me and the other co-founders were out, hanging out one night. We'd all been friends. They both were involved in my previous startup that sold to Intel. And we're sitting around discussing this idea of ZK, and this idea came up of building a circuit that would emulate an existing processor or something else that you could run normal software. And this idea that you could then run ordinary programs in ZK became something, that was sort of the genesis of that idea. And after we sort of did some back of the envelope numbers of where we thought we could get to, realized that we could in fact build a performant ZK VM. That's when we really decided to actually go start the company and go, raise money and do the whole 9 yards. I think that's sort of where RISC Zero came from.
Great. And I think it's very, very incredible that you got your first start when you were 6 years old doing programming. And then you have quite an extensive amount of experience in different fields, not just, say, within ZK, within crypto. You first started in I believe you mentioned ML compiler workflows and then bioinformatics. But it's very, very incredible that you were able to navigate through these different industries and then see where which areas is practical and which areas are applicable. So I think that's really great.
I think with regard to cryptography, I've always been very interested in cryptography, even from a young age. My actual very first claim to fame was actually breaking the encryption on WEP, which was the original sort of Wi-Fi security protocol. which was the first time I ever got sort of publicity and things for things. It was an interesting, exciting time. But I think, and actually my first company was actually doing a cryptographic mesh network protocol, although that was, I think, a little too early. One of the things about startups is it's important to time them when the world is ready and the technology is sufficiently capable that it actually has real world applications. But yeah, I think in terms of the sort of crypto in the sense of cryptocurrencies, I have always been very interested in decentralized and distributed systems. I think that when I first read Satoshi's paper, I thought it was, which I did write shortly after it came out. I was blown away by the idea of solving the sort of Byzantine general's problem effectively in an open network, which had never sort of been done before. And I think it was really, I thought, a great theoretical idea. Although at the time I was like, well, the scaling is only going to get to 4 transactions per second ever. That's effectively not useful, and no one will ever adopt it, was my my thought at the time. Clearly I was very wrong about that, but so I've definitely been following the industry, although this is my first company that's really heavily in the sort of Web3 space, but it's been a very fun and interesting space to get involved with more. So
yeah, definitely. And your point on how timing is very important, I definitely agree with. Sometimes we have the right idea, but the timing, the exact opportunity at that time may not be ready yet. But definitely for the ZK space, we are seeing a lot of improvements over the years. And right now is finally the time where we can begin to see some real world applications, which I'm super excited for. Yeah, I'm very curious to hear. And very curious to hear you. You mentioned that you were exploring ZK specifically for the past 7-8 years. Curious to hear how you've seen the space evolve over the years. How would you compare the space when you first started 7 or 8 years ago to now? Were there any kind of key challenges in the past that have been addressed, or any kind of new challenges that we're currently prioritizing now, and any kinds of aspects that you foresee becoming future challenges in the future, especially as we get some more mainstream adoption?
Yeah, I mean, I think, in terms of the historical challenges with ZK, I mean, obviously, I think for many years, performance was a real issue. And I think that we have since then seen both, a number of sort of mathematical or proof system improvements at a theoretical level, as well as just a lot of practical implementation work. I mean, I think one of, our initial goals as a company was to sort of solve some of the engineering problems that were not fundamental or theoretical, but just, there had been no GPU implementations of these proof systems prior to, our work, right? And so I think that, that had been something that historically had been a big problem for ZK that has now been almost entirely addressed. I think at this point, the existing sort of popular proof systems have reached performance where it's eminently practical for many use cases. And in fact, it's much less expensive to prove something in ZK and verify it on chain than it is to just execute on chain, right? You can actually run Solidity code in ZK for cheaper than you can pay for gas costs, right? So I think that that's, to my mind, sort of one of the critical, points in the performance curve, really, is where you hit that point where it's actually just cheaper to run it off chain. In terms of sort of, other big concerns, I mentioned earlier this usability concern with ZK. And I think that that has also really been addressed with the sort of emergence of, with our work on the ZK VM, and other people's making use of that same kind of concept. I think that one of the interesting things to me, if you ask me where the biggest challenge in ZK is, I think there's actually partially just a awareness challenge, in that a lot of people, I think, became very excited about the potential of ZK and adopted sort of earlier ZK systems prior to sort of the current batch. And ran into sort of issues with performance or programmability. And I think that many people still have a perception that ZK is, in fact, difficult to use, or that ZK is slow. And that's just really no longer the case anymore, right? I think the remaining sort of open questions really are around protocol integration, questions around how do you actually go get the proofs generated, how do you do payment, how do you get aggregation done, how do you do integration on different chains. And really that's with regard to our work. We will continue to, of course, work on, improving the capability and performance of the zkVM itself. But now we're also spending a lot of time focusing on our new boundless, which is basically a mechanism, a universal ZK protocol with the idea of bringing the capacity to get, ZK to run ZK on every chain, right? So how do we make it so that an end user can take advantage of this off-chain computing wherever they're at? If they're on Ethereum and they want to have a proof generated on Ethereum and pay an ETH, how do we make that possible? So that's sort of our next level, is really this question of how do you apply ZK for specific protocols and use cases.
Mm-hmm. And I do really like how you mentioned about the awareness challenge. Like everyone speaks a lot about performance, about programmability, about the usability issues here. But I also do think that the awareness challenge is also pretty critical, and education is pretty important in this part as well. And like what you mentioned, that people still have the perception that ZK is difficult to use, is slow, is expensive. Even though we have these new developments, it's something that's also a barrier. So really appreciate you for mentioning that as well. Also curious to hear about your thoughts on the general kind of ZK endgame. So I'm very curious to hear like what the ZK endgame means for you specifically, and if we compare it to, say, some other cryptographic primitives that we've been seeing quite frequently in this space. Like, for example, with MPC, with FHE. Do you see ZK still being dominant over the future, or do you see like a combination of these primitives being used?
I think that there's a couple of different questions in here. I think let's just talk to the sort of other cryptographic primitives part first. I think that like FHE, for example, I think has a very high potential. But I think that where it is right now in terms of performance it still has not hit that sort of critical juncture where it moves from into this sort of practical usability in the same way that ZK has, although it could be getting there very soon. I think that in my mind, there still needs to be a little bit more sort of research or improvement on the math side. It's not just an engineering problem yet, but it may well move into that position soon, at which point I do think there are certain use cases where it's the right sort of solution. Honestly, I have not been following the sort of mathematics in that field nearly as well since I've taken over as CEO. I have a little less time to read math papers than I used to. So I think the jury is still out on that. I mean, I think in terms of sort of ZK endgame, in my opinion, most execution is going to move to ZK for all sort of distributed systems or blockchains. I actually think that right now we've already crossed that critical cost threshold where that's less expensive than effectively the cost you end up paying for consensus of re-execution. And I think that is going to accelerate. I think that additionally, the fact that you can, once you move those sort of computing workloads off-chain, you move away from this sort of scarcity world where if you look at the existing sort of blockchain execution paradigm, the way that it works is that there's a fixed amount of gas available per block. And if there's a higher demand for execution, there's a fixed supply, and so the costs go up, right? And you you really can't do that much computing before gas costs start to rise too extensively. Now you can, to some extent, move things to L2s or roll-ups or other types of systems, but then, that same problem will reoccur in this new consensus domain, right? Whereas when you look at the sort of, ZK case, there's really no limit to the amount of computing that you can do off-chain, and the costs per compute doesn't go up as the demand goes up. As the demand goes up, the costs remain at the cost of the compute. And so you have this much more sort of, you go from this sort of scarcity to abundance kind of a mentality with regard to compute. And as we've seen, whenever there's more room for compute, that compute just gets filled up with more useful use cases, right? So I actually think that the other real thing, besides a lot of this sort of compute moving off chain to ZK, is we're going to start seeing much more rich sort of applications being developed because they're no longer sort of compute bound, right? And even longer term, I actually think you'll see sort of in some ways this modular notion of moving data availability to outside systems. You're going to move compute to sort of ZK, and then I think we're going to see some interesting work done on sort of consensus and sequencing. There's some work I think that's quite interesting on sort of causal ordering instead of doing fully sequenced, and some other things that can improve the overall bandwidth of these types of systems. So I think there's quite a lot that's going to happen in blockchain over the next couple of years. We're very much focused on the ZK and the sort of off-chain execution side of it, but I think that we'll continue to see these other developments have an impact as well.
Mm-hmm. And I really like how you mentioned that mentality from scarcity to abundance as we're seeing the ZK for compute especially. Really like that comparison. Also curious to hear, since you've dabbled in some other industries, like you've had startups in the bioinformatics space, in the ML space. I'm wondering if you see any kinds of major takeaways from the ZK space now, having RISC Zero. Do you believe can be applied to some other industries, some other areas, especially where usability is initially questioned? Are there any kinds of takeaways that can be applied to some other industries?
Yeah, I mean, I think I guess just to clarify, are you asking more about like how ZK can affect other industries outside of blockchain, or are you asking more about sort of how other industries have similar? There's other industries where we are at a similar juncture with regard to where ZK was a bit ago.
More of the latter, but also the former. It's also an interesting question. Well, so if you want to address both.
Certainly. I think it's always interesting. There are always these sort of threshold points. We've seen this over in lots of industries in the past. Like, so for example, in ML, obviously it's a huge industry at this point. And what's interesting is I was actually watching a lot of this even from the early 80s, right? Neural networks were something that had been experimented on, and I actually remember reading some of Hinton's early papers on backpropagation and trying them out, and it was cool, but it didn't scale in a meaningful way, and so there was a very finite limit as to how well it would ever work, and then it was not, and that limit was not above the sort of critical threshold to be applicable, right? And you watched how there's continues to be this background research effort that's ongoing, and this continued work and this continued progress, but it doesn't really affect much of anything because there's this sort of threshold you need to reach before something becomes economically meaningful, right? And we sort of crossed that threshold with sort of the early deep neural networks and their sort of ability to do vision processing, and then very rapidly you see this money flow into the sort of development and engineering of these research ideas into real products, as well as a massive expansion in the amount of research being done in that field, which leads to sort of the field moving from sort of this nascent industry into like a real industry. As for what the next industry is that's going to make that, and I think that in each field there's a difference in terms of what those barriers are. In ZK, right, the performance was a barrier, and the usability was a barrier. What the sort of next nascent industry that's about to move into that sort of production level is, I don't have any great investment advice in regard to that myself right now, but I do think that ZK is firmly it's firmly across that line, and I do think that I think, for example, the discussion within the Ethereum community has very strongly moved to this idea that of course everything is going to be proven in ZK, and that this is the direction that things are going. And I think it's interesting to note that community has definitely looking toward the sort of ZKVM direction. I think that was one of the sort of major factors that made all this practically applicable. So I think what was there was a second half to the question. I think I've lost track of it though.
Oh yeah, no worries. Also, like ZK beyond the Web3 space, do you see ZK also being applied to some other industries? Mm-hmm.
So I actually think my personal thesis on this is that ZK is going to long term be as significant of a technology as, say, public key encryption, that it's going to be something that every computer science student learns in their freshman year, the basics of, and then no one will need to know the inner workings, just the sort of high level concepts, right? At this point, people you go to your web browser, you type HTTP or HTTPS, and in one case you're using everything encrypted. It's almost transparent to the end user. It's just sort of built into the fabric of things. But that technology was really critical to allowing secure transactions over the internet, without which the entire infrastructure of e-commerce and all these other amazing things that we take for granted wouldn't have been possible, right? So similarly, I think ZK is going to become a core technology across all of computing, because it fundamentally changes the trust model between parties when it comes to computation, right? I can now let some random person run a computation and completely trust the results, which historically has never been possible, right? There's an adage in the Web 2 world that, well, you can't trust the client. Well, with ZK, you actually, in theory, could trust the client, right? And as we continue to develop the technology and client-side proving becomes faster, as the rest of the world sort of becomes aware of this, right? I think actually a lot of the non-Web3 use cases are just limited by there's just a lack of awareness, right? I think the Web3 industry has a deep understanding of ZK because it's been being discussed as a part of scaling for many years. I think that the awareness of the properties of ZK are not really. If you talk to some random, developer in the Web 2 space, they often don't even know that it exists, right? So I think as that becomes more common, we'll start to see an expansion. And actually, I think there's some really interesting use cases already emerging today. For example, one of our partners, Hashflow, is working on has built effectively a centralized but verifiable exchange, right? And the idea here is that rather than actually having a fully decentralized system, you can in fact have a centralized system and all the advantage that you get from that, including a private centralized system. So you get high transactions rates, you get good UX, you get this ability for the exchange to have private information, but you're effectively using ZK to verify the correctness of the exchange, right? So you could prevent things like what happened with FTX from happening, because effectively, in some sense, you can be auditing the exchange continuously and in a way that the results of the audits are effectively public, while still maintaining privacy. These kinds of use cases are really fascinating to me, and I think that we're going to see the emergence of a huge set of new use cases from ZK, even outside of the sort of the Web3 world.
Definitely. And just wanted to go back on your point before on usability and how that was a very big challenge within the space. And that was kind of one of the main driving factors for focusing on specifically a ZKVM, because now developers who don't need to know how to write circuits can now, generate proofs from programs. Very curious to hear about your take on ZKVMs versus circuits, any kinds of trade-offs that exist in them in terms of performance, in terms of time to market, in terms of developer experience. Has been quite a heated discussion recently on if one will become more prevalent than the other in the future. So very curious to hear about your takes on the like trade-offs between them.
Yeah, I mean, I think to me, I actually think the analogy of ASICs is actually a really fruitful one in this particular case, right? So if you look at the historical development of semiconductors, right? Once upon a time, every application had its own independent ASIC, right? There was a time when, for example, a vending machine, there was actually a custom chip built for vending machines that had pins that were like quarter, dime, nickel, where you'd send a signal from the actual change part of it to this custom ASIC, which would then have counters in it that would, add up the numbers and decide whether you'd put in enough money to pay for a can of soda, right? And with the emergence of the microprocessor, almost all of those kinds of things went out of existence because the microprocessor was general purpose enough that you could solve all these problems by just writing code. And, the idea of building a custom ASIC for, a specific use case now at that level of use case is considered completely ludicrous. I think, though, there are still places where custom ASICs make sense, right? Like there are a number of people who've built custom ASICs for, ML use cases, or, obviously the GPU is an alternative to the CPU for different kinds of computing, right? It's also quite general purpose, but it has a different architecture because the needs for some use cases are different. So I think that in that regard, there will be places where it's worth building sort of custom circuits, or more likely, sort of, we call them accelerators, but I think the more common developing term is precompiles. But we've had, for example, an accelerator for SHA-2 in our ZKVM for the entire time. We're about to put out a precompile, if you will, for Ketchak. We're also adding support in the 1.2 version of our circuit for a general purpose programmable algebraic accelerator, which will allow many big integer operations and elliptic curve operations to be run much more quickly. I think this is a lot like this is very similar to the case of ASICs, right? As time went on, you saw general purpose processors add specialized instructions. You saw specialized coprocessors. And so I do think there was always cases where the performance of a circuit makes sense. But I think the idea but I think in almost all those cases, it's going to be orchestrated or run by a ZKVM, by like a microprocessor kind of a model, right? If you look at almost everything in it has a microprocessor, even if you have some custom circuitry, the majority of your logic doesn't need to be fast. It just needs to be easy to develop and, easy to audit and verify and easy to continue to update as you need to add new features. And then, yes, if there's a couple of places that need very high performance, you might want to go down to the next level. But it's going to be the minority of, if you look at most programs, 90% of the code is very low in terms of its impact on performance, and there's some small inner loop that accounts for 80% of the runtime. So maybe that small inner loop is worth building into something more like a actual circuit, but the rest of it is much better done in sort of a software model, in my opinion.
Mm-hmm. Got it. And are there any specific scenarios or examples that you can think of where it'd be particularly advantageous to use the circuit-based approach versus the ZKVM-based approach, and vice versa, where it's more advantageous to use a ZKVM versus writing out the circuits directly?
Yeah, I mean, I think on the few cases where the circuits do matter, it's really mostly around dense cryptographic operations that are important for the blockchain. Things like cryptographic hashes, public key cryptography systems. And then I think also there are certain use case specific things like ML, for example, I think makes sense to I think, again, to the extent that these things are custom circuits, I think they're custom circuits that are built to integrate with a ZKVM. Like there's some, like if you're building a image processing system using ML in ZK, probably the core sort of network itself, the actual the actual deep neural network likely be something that has some circuit acceleration. But the image decoding, you want to decode a JPEG, That's crazy to do in a custom circuit. Much better in a ZK VM. So yeah, I think those are mostly the cases where this custom circuit kind of approach will still continue to be meaningful. But I think almost everything else is much better off on the ZK VM. And we've seen a little bit and I think there's a little bit on the client side. We've seen this idea of client side proving. There's still a lot of use of custom circuits on the client side proving, largely because of performance. It has to be super good on the client side, but I do think that we already have done some experiments with client side ZK VMs, running our proof system on the iPhone, and we're not ready to productize any of that yet. But I think that the client side being circuit based is also just sort of a temporary artifact of the engineering not being quite where it needs to be yet. But I think that will get over the line as well.
Got it. And I do want to transition into more RISC Zero specifically. Very curious to hear about what was the original vision behind RISC Zero when you first co-founded it, and how did it evolve over time to today?
I mean, I think that's interesting. I think the original vision was really around bringing ZK to the world in a real way, making it something that was practical. I think that vision is still largely the case. I think that what we're working on technologically has moved from originally the core proof system and the ZKVM to now where we're really focusing on the network level and boundless, and how do we sort of bring ZK to every chain in a way that's almost transparent to the developer. But I think, our entire time, the focus has been bringing the promise of what ZK could be into reality, right? Like when I first read those early papers on ZK, like I said, my mind was blown. I was like, I can't believe this is even possible. And wow, if you could really use this, all the cool things you could do. But it wasn't, from a practical perspective, it was way too difficult, way too slow. And, I think that, really our mission has always been to bring these things to the point where they're practically applicable.
And I think that's really the vision for all of the ZK projects in the space, trying to make it a reality, trying to make it so that we can enable these real world applications. So we're in a time of innovation. It's very, very exciting.
Yeah.
Also,
I was just going to say, one other thing with regard to that, I do think that, if you look at what the value of all of this is it's really about being able to do. I think the privacy components are significant, but I think also this sort of idea of verifiable computing, is really like, in some ways, the blockchain is predicated on this idea of verifiable computing in a similar way, in that this idea that you can know some computation was done correctly because many, many, many people have looked at it. And ZK allows you to know that some computation was done correctly just because math. And so it's actually, in some ways, one of the huge promises of ZK is to absolutely get rid of all of the scaling limitations on compute in the blockchain space, which I think it is actively. I think we're going to see that happening. The next year, I think, is going to be. We're already seeing real-world applications of ZK going into production. I think by the end of this coming year, a huge portion of the execution being done in these decentralized systems will all be done in ZK.
Mm-hmm. And it's really great that you distinguished kind of the different uses of ZK as well. Like, we have the privacy component that everyone's very excited about, but then there's also the verifiable computation aspect, which is also pretty powerful. Thank you for mentioning that. And also wanted to speak a bit about the kind of the developer experience, because I know that's something that RISC Zero is very keen on focusing on. Curious to hear what you see as the biggest pain points that developers face when building with ZK, and how RISC Zero is helping to make ZK more accessible and improve the general experience.
Yeah, I think in general, the developer experience has gotten much better with the emergence of ZK VMs. it is now generally the case that you can just run some Rust code. I do think, interestingly, on the Web3 side, Rust is not a language that everyone is as familiar with. So one of the, we have Steel, which basically allows you to run existing Solidity contracts inside the ZKVM, and in fact actually make use of on-chain state. So you can actually execute Ethereum contracts on Ethereum state in the ZKVM, which I think makes it even more accessible to other developers. And I think these sort of mechanisms to bring that usability even further are obviously going to be part of the sort of direction that Boundless is going. I think that there are still ways to go in terms of even the sort of core ZKVM. We are working on a V2 version of the circuit that will provide a much broader range of compatibility with existing software, not only the Rust ecosystem, but a wider set of languages as well. And I think that. I think there's also things to be done in terms of making it easier for people to deal with a lot of the work on. Even if you do have a ZKVM, you're still operating on a sort of more limited computational machine than people are often used to. If someone's been familiar with doing work in embedded development, then it's generally quite easy. But for people who've only sort of written higher level languages or things like that, there's still room, I think, to make significant improvements. That said, I would say on a usability side, it's night and day from where it was a year ago, and I think that to many people we've had pick things up and get their projects working in a very short amount of time. So I think there's a lot of just how quickly can you make the installer. We've moved on to very block and tackle usability kinds of concerns at this point, and we're going to continue to do those. I think those are super important, but they're also pretty well understood things to improve on.
Got it. And also wanted to speak a little bit more about Boundless, which you've previously touched on before, but you speak of the vision in providing verifiable compute through ZK for all chains. Curious to hear what the implications are, how this entails in terms of interoperability between these chains, in terms of global composability, and maybe you can touch on some issues that currently exist with our current fragmented ecosystems. Just curious to hear about the implications that you see happening with Boundless.
Yeah, absolutely. I mean, I think we are going to be moving as an industry, I think, into a continually, more sort of cross-chain and interoperable computing. And I think that one of the things that ZK allows is it allows one chain to be able to access the state of other chains via, ZK consensus and correctness proofs, as well as to be able to, prove that some state exists in the state root of some remote chain. So I think that we're going to see that become much more common. And additionally, I think in terms of Boundless, the way to really think of it is that we're providing this sort of computing infrastructure that exists across all of the chains, where proofs can be reused on multiple chains, and the accessibility of this computing infrastructure is addressable from all of the different chains, right? So the design of Boundless really sort of has these sort of core services and then this sort of set of extensions. And the core services include things like the proving marketplace to allow people to basically pay for proving, aggregation mechanisms to allow for those proofs to be aggregated for much more efficient, on-chain things, and as well as the settlement mechanisms necessary for the payment. And then on top of that, I think there's a lot of that we're developing, and our partners are developing a number of different sort of extensions to basically make specific use cases much more addressable. So, for example, we have Steel, which allows you to run sort of smart contracts off-chain, or Kahlua, which allows you to sort of make use of this for sort of ZK optimistic use cases. When these kinds of there's a number of things being worked on with regard to sort of some cross-chain functionality. There's sort of this series of, and we have a number of partners working on things like, for example, making it easier to integrate with, ZK email, or work being done on the Solana ecosystem for running Solana contracts off chain and things like that. So I think that, I think that we're gonna, I think one of the key things is, though, that these capabilities will exist across multiple chains, and it will help sort of create this availability of compute resources that's part of like a global, non-chain specific resource, right? Which, by the way, interestingly, none of our stuff introduces any new consensus domains or anything like that. So it is really, truly both decentralized and censorship resistant, and has a properties of scaling that are not limited by consensus. So, as there's more demand, it's very, very easy to, you effectively have this sort of on-demand, scaling of compute capability.
And part of the boundless stack also includes like a decentralized proving component. Also very curious to hear if you can speak about the advantages that decentralizing the provers provides in terms of like what you mentioned before, censorship resistance, liveness guarantees, and also curious to hear if there's any kinds of trade-offs between having like centralized provers versus a decentralized prover network.
Yeah, I think in general, we believe very strongly in decentralization, and also many of the use cases, the best use cases for ZK are to help add this capacity to systems for which decentralization is a critical feature, right? And of course, if you are reliant on some centralized proving infrastructure, you've sort of thrown out the baby with the bathwater, right? Like there's no point in making a decentralized system that depends in a fundamental way on some centralized system. I do think there are still lots of use cases for centralized provers for certain use cases. Obviously, for example, if you have a centralized exchange that wants to be a verifiable centralized exchange, they could absolutely use a centralized proving system if the costs made sense for that relative to sort of a decentralized use case. Although we strongly anticipate that the existence of an open and free market for proving will result in some of the best costs. I suspect that the decentralized system, from a cost perspective, may end up being less expensive than the centralized systems. Although there's economy of scale arguments in the other direction as well. I guess that we will the market dynamics we will see how they all play out in practice. But yeah, I think I think that, in my opinion, true decentralization is sort of a minimum bar that's required for a lot of these use cases, including full censorship resistance. And so that's what we're really are. We have an existing internal test net, which has a number of our partners have already been generating proofs on, and a number of provers that are not us are also running on producing proofs, and that we already are fully decentralized. So I think unlike we're not going to sort of go with a progressive decentralization model or anything like that. From the first public test net to all the way to mainnet, we're going to be fully decentralized the entire way.
Just a quick follow up with that. I know with the concept of decentralized proving, especially for verifiable computation, a lot of that can be offloaded. But for a privacy component or a privacy first service, some aspect of centralized proving might be required. I guess you mentioned briefly that you want to focus on a decentralization first perspective. In terms of the privacy preserving component, do you see there being certain types of optimizations that you would be prioritizing for to enable essentially better performance for potentially client-side proving, maybe with specific hardware requirements, even if that does come at a cost of centralization?
Interestingly, there's a couple of different approaches on the privacy side. I personally believe that for privacy use cases, the long-term direction that we'll land on is client-side proving for the privacy sensitive components, and sort of open public proving for much of the protocols. In a lot of these cases where there's a privacy concern, only a small portion of the protocol needs, like let's take a look at like a private currency transfer, right? Like generally the main part that's privacy sensitive is sort of the lookup in some Merkle tree to verify that some value exists in that Merkle tree, and that portion could be moved to sort of a client-side proof, and then the rest of the protocol could run in an open network where these sort of privacy, the provers don't need to have access to private information. So because of proof composition, it's possible to really restrict the sections that are privacy sensitive to very small components, and I think that client-side proving is rapidly speeding up. There are other alternative mechanisms. Our proving marketplace allows you to only allow a certain set of provers. So if you, for example, trusted some set of provers to hold your data in confidence, you could use a mechanism like that. There's work being done on doing proving inside of T's for privacy, trust execution environments, right? So I think that there are other approaches certainly, and those may end up being also highly relevant. Although I do suspect long term that to really answer privacy in the strongest way, I think getting client side proving to be sufficiently efficient and programmable is going to be one of the major sort of stepping stones in that regard.
Mm-hmm. And I do want to dive also into the ZK optimistic use case that you mentioned with Kailua. I'm wondering if you can touch on the value proposition behind combining both optimistic and ZK into a hybridized approach, and the kind of limitations that exist to solely using, say, optimistic rollups, solely using ZK rollups. Just the value proposition that happens with this hybridized approach.
Absolutely. I mean, I think if you look at the existing optimistic stacks, right, the fraud game that is used and the sort of cut and choose mechanism that is required to sort of do a challenge and verify whether some particular optimistic statement was fraudulent or not is just a very complex process that requires a lot of back and forth on a public channel where censorship, resistance requirements imply just a lot of stages, and because that is expensive, that process of doing the challenge and the verification, it also just leads to it being expensive to challenge and the staking requirements being higher. Just the whole process, right? What's interesting is that you can sort of determine in one shot with ZK whether a particular statement was correct, and not only that, but also provide what the correct statement was if it was wrong. And so even if multiple different challengers want to challenge a particular block or say that the answer is different things, you can terminate all of that rapidly with a single shot in ZK. And so it allows you to sort of really make big improvements on that. And in terms of this hybrid approach, I think in the not too distant future, maybe even now in some use cases, it does make sense to do full ZK validity, but it is still more expensive than the sort of optimistic approach. And what's interesting is that you can actually build these very interesting. Not only can you sort of make use of this hybrid for the challenge process, but you could also, for example, allow earlier withdrawal from the system by allowing a user to provide a zero knowledge proof from the beginning of the current window until the present. So, for example, if I'm a user and I have I want to do a withdrawal, and there's a 2-hour window or what have you, I can just prove the entire state of the last 2 hours up until my transaction, and then do an early withdrawal, right? So there's this case where you can argue for the payment of the ZK not being on the L2's dime or as part of the general transaction fees, but as specific users, as like sort of a way to move from optimistic to ZK. And I think we really believe, though, we're not, as a company, we also love ZK validity proofs. And actually, I do think that long-term, as ZK continues to reduce in cost at some point for many systems, that's going to be the right answer. But we really want to provide, users and people building systems all of the available options. And I do think that this sort of combination of optimistic and ZK is a really compelling and interesting place in the space of all different trade-offs of economics and usability, et cetera.
Mm-hmm. And I do like how you mentioned that your focus is on providing users with that kind of choice, navigating through those trade-offs, like if they want to use like solely ZK or solely optimistic, combination of the both, depending on their needs. So really liked how you mentioned that. Also curious to hear if you could shed some light on some of the motivations and reasonings behind the architectural considerations of RISC Zero ZK VM. Like, for example, you guys used Fry-based prover, used Groth16, and you also haven't mentioned. I remember reading an article that you guys wrote about some of the motivations behind the design and how there are some cutting edge research, for example, within folding schemes, but then you chose not to adopt it as of yet. So curious to hear some of the reasonings and motivations behind the design that you've adopted so far for your ZK VM.
Yeah, I mean, I think, in terms of the adoption of Fry or sort of, small field commitments, really it comes down to, particularly in the case of Fry, because the design of the ZK VM is fundamentally sort of an iterative process. The way that Fry is structured lends itself very well to performing the same computation over and over in a iterative fashion. In fact, in many ways, the way that error constraints are designed looks a lot like transition functions in digital circuits, right? It's actually really naturally aligned with sort of a VM-based system. I think, and in terms of Groth16, largely we chose that due to performance characteristics, both on proving and on verifying on chain. Obviously, Fry-based systems, of course, are very, very fast at proving, but where one of the concerns is the size of the proof is quite large, which is really, and actually not only Fry-based systems fast at proving, they're also fast at recursion. But again, the size of the resulting proof limits the applicability for on-chain use cases where, putting 200K worth of proof data on-chain is not really feasible. As a result, we need to use a different system for sort of these on-chain use cases. Groth16 is both efficient concretely on the proving side and efficient on the verifier side on-chain. And so really that was largely based on, performance, and also it's very well understood, it's a very low risk choice in some sense. I think in terms of, there's a lot of very exciting new developments at the sort of proof system level, and we do continue to track those. And we are looking at sort of what our next generation version of our proof system will look like. That said, most of the advancements that have been made since sort of our original version of the proof system, while they are, are improvements, in many cases, when you actually go and do the back of the envelope numbers and look at how well they would perform on the GPU and how easy to parallelize they are, and actually sort of look at the engineering, estimates of where the performance deltas you would get from them, you're looking at oftentimes, 30% improvement, 50% improvement. And the truth is that we're still in a regime where just plain doing better engineering on our existing system has been yielding us, very significant. I think we're like well over 5x faster than we were, a couple months ago, just based on just these sort of engineering improvements. And so, we are anticipating applying some of these other changes to the proof system, but effectively, from a practical perspective, where things are right now, there's just lower hanging fruit, to be honest. I think that, there's also a little bit of you do want to wait a little bit after research comes out, both from the perspective of having better peer review, making sure there's no issues, but also because, maybe next week an even better idea will come out based on that idea, right? So there's always sort of a timing issue in terms of so we have been working on sort of what our vision is for sort of the next generation proof system, but I think largely we've been very happy with what we've got so far.
Got it. And it's always very interesting to hear about kind of the thinking approach that you take with deciding, say, which proof systems a project is using, or what kind of design considerations that they're taking on, and how you go about with navigating through those trade-offs. So, really interesting to hear. And also curious to hear some of the long-term developments for RISC Zero in the next couple of years, and how you see it evolving.
Yeah, I mean, I think our biggest, of course, thing that we're working on is sort of boundless and making that a reality. If we look at sort of the ZKVM, though, there's a lot of exciting work getting done on that. We're building a version 2 of our circuit, which will have a lot of additional functionality, which will, I think, make it possible to use for a much wider set of existing software. And just also significant performance improvements, much larger guest memory, these kinds of things. We also have been doing a lot of work on sort of, precompiles and accelerators, including the 1.2 release is going to be coming with a sort of effectively a fairly general purpose cryptographic coprocessor for any kind of large integer operations, which is based on sort of some novel work we've done internally, which we're quite excited about. But also, with the Zergen DSL, we're working on making it easier for third parties to build custom circuits for areas where they need those types of things. So I think there's a lot of sort of ZKVM improvements that are coming out over the next year. I mean, I think if you look 2 years out or 3 years out, I think the industry is still moving fast enough that it would be very hard for me to make meaningfully useful predictions, since it's very possible the math may change between now and then. Although I would note that the new ideas that lead to massive performance improvements, these sort of 10x wins we were having with sort of the mathematical structure of things for a while, have slowed down. We may, in fact, be getting close to the bedrock there. It's hard to say, though. Research is always unpredictable, and there's definitely a lot of energy going into research, which means that you can expect more to come, I'm sure.
Yeah, very exciting times that we're in, indeed. Lots of new research popping up every day, and there's just more to come, which I think is super exciting. But just as a last question before we close today, do you have any other announcements you'd like to make, or any sort of advice or last takeaways you'd like to give to the audience?
I definitely would say everyone who's interested in using zero-knowledge proofs for anything to take a look at Boundless. We are, onboarding developers at this point into our private testnet, and the public testnet is coming soon. Beyond that, no, I think we've covered most of everything. So.
Yeah, thank you so much, Jeremy. Yeah, really great to hear from your vision to the space, to even your background, first starting off with loving to read math research papers and then diving into these different industries, and then now focusing on ZK, and then your current developments with Boundless, with Kahlua. So very great to hear all of that, and really appreciate you for being on the podcast here today.
Absolutely. Well, it's great to talk to you as well. And yeah, have a great day.
Yeah, thank you so much, Jeremy.